Self-driving cars already use some pretty advanced technology to understand the world around them. Most autonomous vehicles rely on a combination of cameras, LiDAR, and radar to detect roads, pedestrians, and other vehicles. Cameras help the car visually recognize objects like traffic lights and people. LiDAR sends out laser pulses and measures how long they take to bounce back, building a detailed 3D map of the environment. Radar, on the other hand, works using radio waves, a bit like how bats use echolocation, allowing vehicles to measure distance and detect objects even in poor lighting or bad weather. Each of these systems plays an important role, but none of them are perfect. Cameras and LiDAR can struggle in rain, fog, or low light. Radar is more reliable in those conditions, but it has its own limitations. Radar works by sending out radio waves and waiting for them to bounce back from objects. The problem is that not all of those waves return to the sensor. Many scatter in different directions, which means the vehicle only receives part of the information it needs. Because of that, some objects can easily go unnoticed. A pedestrian stepping out from behind a large truck, a cyclist around a corner, or hazards hidden behind obstacles might not be detected in time. Even when radar does detect something, the signal can be weak or unclear, making it hard for the vehicle to figure out exactly what it's looking at. As autonomous vehicles become more common on roads, safety expectations are getting higher. What used to be seen as minor technical limitations are now considered serious challenges that engineers are working hard to solve. Researchers at Rice University, led by Kun-Woo Cho, are exploring a new idea that could help improve how autonomous vehicles sense their surroundings. Instead of relying only on sensors mounted on the vehicle itself, they've developed a system called EyeDAR that places radar sensors on roadside infrastructure. These sensors could be mounted on things like traffic lights, road signs, or billboards. From those positions, they can capture the radio waves that normally scatter away from a vehicle's radar. By collecting that extra information and sending it back to the vehicle, the system can help cars build a much clearer picture of what's happening around them. The device itself is surprisingly compact, about the size of an orange. It works using two main parts that function a bit like an eye. The first part is a special type of lens called a Lundberg lens that focuses incoming radio waves. Behind that lens is an antenna array that detects the direction and strength of those signals and relays the information back to the vehicle's radar system. One of the most interesting aspects of EyeDAR is how it processes signals. Traditional radar systems rely on large antenna arrays and powerful digital computers to interpret the incoming data. EyeDAR takes a different approach. Its lens is made from a metamaterial structure composed of more than 8,000 tiny elements, each carefully shaped and positioned. These microscopic structures are designed to bend and focus radio waves in specific ways. Because of this, the lens itself performs part of the signal processing physically as the waves pass through it. In other words, the material acts like a built-in analog processor, analyzing spatial information at the speed of light before the data even reaches a computer. During testing, the system was able to determine the direction of targets more than 200 times faster than conventional radar designs. Another interesting detail is that EyeDAR doesn't generate its own radar signals. Instead, it collects scattered waves from existing radar signals and redirects the cleaned-up information back to the vehicle. The researchers believe this approach could make it possible to build networks of these sensors across roads and highways, giving autonomous vehicles a much wider and clearer view of their environment. Not everyone is convinced it will be easy to roll out at scale, though. Some experts point out that manufacturing the lens requires extreme precision, with thousands of microscopic structures that must remain perfectly shaped while exposed to sun, rain, and temperature changes. Producing these devices reliably outside a lab environment could be a major challenge. Even with those concerns, the concept has a lot of potential. A network of roadside EyeDAR sensors could allow vehicles to detect hazards far beyond the reach of their onboard sensors. And the technology might not be limited to cars. Similar systems could eventually help drones, robots, and other autonomous machines navigate complex environments more safely and efficiently.